All right, so starting a new week, starting a new section of the course, where are we? We've talked about what I maybe in this slide are calling informatics. So the management, manipulation, integration of data, and we had some emphasis on scale, and we had some emphasis on specific tools. Okay, so now we're moving into what I'll call analytics. And so we're going to talk about statistical estimation and prediction. And one of the points I want to make is that this builds on the informatics, in that the things you're going to learn you can implement using the tools before. And we already saw a piece of this where we did sort of matrix multiplication and various tools and so on. Okay. The other point, if you remember, we made early on was that 80% of what people think of as analytics really boils down to the ability to do sums and averages. And so we'll see a little bit of that in here, where maybe understanding the problem and understanding the solution is hard or easy depending on maybe your background. But as far as implementing it, it's not too bad. Okay. And then we'll move on to the visualization in a couple of weeks. All right, so to get started on this, I want to call your attention to this article in 2010 from the New Yorker, with the caveat that this is far from a research article. And in fact, a lot of what the article has to say, I'm not sure I'd recommend taking to heart. But the point, the topic that they bring up is that the title is here is "The Truth Wears Off," and what they're exploring is this notion that statistical results in the sciences seem to have gotten weaker over time. And so John Davis is a researcher at the University of Illinois who does work on antidepressants, is quoted and is discussed as talking about how a forthcoming analysis is demonstrating the efficacy of antidepressants has gone down as much as threefold in recent decades. So this is that the effectiveness, as measured by clinical trials, of these antidepressants has gotten a lot weaker. The article also talked about Anders Müller, who studied barn swallows and discovered that the females were more likely to mate with males that had long symmetrical feathers. And this finding sort of relied on precise measurements of the symmetry. And so this was a pretty significant discovery, but over the course of the next 5 or 6 years, the effect size, as discovered by himself and other researchers, shrank by 80%. Okay, a lot of the article talks about Jonathan Schooler in 1990, who made a discovery of an effect that he called verbal overshadowing, which was counterintuitive because it showed that people who are asked to describe a face, using English that they've seen, were actually less likely to remember it than those who had just seen the face. And so talking about the face somehow overshadowed the effect of just seeing it alone. Okay, and once again, this effect seemed to get weaker over time and became increasingly difficult to measure, but including by Jonathan Schooler himself. And in fact, he's quoted as saying this frustrated him, right? He was having trouble replicating it. Okay. And then they also bring up someone who's a little less respected, a fair amount less respected in the scientific community as an historical example, and is the person who actually coined the term the decline effect, which is brought up over and over again in the article. So in the 1930s, Joseph Rhine tested individuals with these card guessing experiments in an attempt to measure the effect of extrasensory perception, or ESP, and he's the one who actually coined that term. So he had a few students that achieved multiple streaks of very low probability, many cards in a row that they guessed right and so on. But there was a decline effect, and that the same candidates, the same participants, couldn't match their earlier performance. Okay, and so the article touches on what is essentially the correct explanation of this effect, and it also sort of brings up the possibility of a bunch of quasi, mystical, incorrect explanations of this, at least in my opinion. So I want to tell you about, I want to, in the next couple of segments, next few segments, I want to sort of explore this as a test case for statistics and statistical estimation. And I want to use this as a vehicle to introduce the fundamental concepts of statistics and also some of the somewhat more advanced concepts of statistics especially as they relate to big data. Okay, so to get started, let's talk about the background here, and then we'll come back to this specific article and explore the reasons for why the truth wears off. Okay, so this is not going to be a replacement for a introductory college statistics course. This is going to be a quick overview of the terminology and the concepts you should be familiar with. Okay, so we're talking about statistical inference here, and so these are methods for drawing conclusions about a general population from sample data. And there's two key methods that you can use here: hypothesis tests and confidence intervals. And we're going to bring in confidence intervals again a little later on, but I'm not going to talk about them directly right now. All right. So what is hypothesis testing? Well, you're going to be comparing an experimental group to a control group. And there's always going to be a null hypothesis. And the null hypothesis is there's just no difference between these two groups, right? The one who received the treatment in question are no different than the ones who did not. The new website generates no more traffic than the old website, than the control website, than the default, and so on. Okay. So that's the null hypothesis. The alternative hypothesis is that there is an effect. There's a statistically significant difference between the two. And so here, difference is defined in terms of some test statistic. And you can, most of the examples you'll find in an introductory course, or really any course, are going to be about comparing the means, right? So the average effect in the control group was different than the average effect in the experimental group. Okay. Now, a lot of what statistics is about is actually designing the experiment to collect the data. And in a data science regime, in a big data regime, we're actually less frequently in a position to design the experiment in the first place. A lot of times we're dealing with data that we did not necessarily collect. Okay. So that's maybe one difference between classical statistics and the way I want to present this material for purposes of data science. Okay. That being said, it's important to understand that careful experimental design is really the most important thing there is in all this work, right? The analysis techniques are second fiddle to the proper collection of data. Okay, so this includes things like randomized trials, blinded and double-blinded. So, what is blinded? It means that the participants themselves don't know which group they're in, and that's pretty much non-negotiable, right? You can't tell people that they're getting a placebo drug versus the actual drug, or they'll they'll report their symptoms differently as an effect. Randomized is also would be non-negotiable, except the fact that it's difficult to achieve in practice in some cases. So randomized would mean we draw a sample through some method, and then we assign them to the groups, to the control group and the experimental group, with no process whatsoever, right? It's just purely random. Okay, so this framework, expressed in just these sort of few bullets at a high level, is unbelievably powerful, right? It's completely universal to data analysis, so it's really important to sort of internalize these points, and we'll go into some more detail on some of the other aspects that aren't included in this slide. So some examples you can dream up, that measuring the effect of a new ad placement on your website compared to the control group of the existing placement, measuring the effect of a treatment against a sugar pill or the best existing treatment, okay, and everything else you might imagine. So to summarize hypothesis testing, you can organize this terminology into this grid here, where there's two possibilities for this true state of the world. One is that the null hypothesis is true. There is no difference between the control group and the experimental group. And the other is that the null hypothesis is false, that there is an effect that you're measuring. Okay. And so then there's also two possibilities for the outcome of your statistical test. In one case, you do not reject the null hypothesis, right? You find no evidence that there's any difference between the groups. And the other is that you reject the null hypothesis. You do find evidence that there's difference between the groups. Okay. So if the null hypothesis is true, there is no difference, but you detect a difference, that's a type 1 error, and the rate at which that happens we will refer to as alpha, and that might come up at times as we have this discussion. Right. And if you make the correct decision, then the probability of that is 1 minus alpha. when the null hypothesis is true. When the null hypothesis is false and you fail to reject it, right? There is an effect and you fail to measure it. That's a type 2 error, and that's beta. And when you do reject the null hypothesis, when it's false, right? You detect an effect when there is an effect to detect. That's 1 minus beta. And this is called the power of the test, the statistical power.